Okay, so chapter 7 here is dealing with exponential functions and doing some graphing with it. And some of this isn't going to be brand new because we've done graphs of these things before. We're going to work a little bit with transformations on them and do some problem solving with it. So basic exponential graph. So y is equal to 2 to the power of x. If you were to do a table of values for this, using your x and y, just using what you remember with laws of exponents, if x was equal to negative 2, then that would be the same as saying 2 to the power of negative 2. That negative exponent causes this to turn into a reciprocal, and then you square it. So this would be like 1/2 squared, so it's 1/4. If I did a negative 1, 2 to the power of negative 1 is just a 1/2. If I did 0, 2 to the power of 0 is just 1. And again, if I could have went bigger. I could have went 2 to the power, or, well, not bigger. I guess it'd be a smaller number, but if I went 2 to the power of negative 3, then my answer would be 1/8. So my power, when it's getting smaller, causes my number to get smaller. And then it gets until it hits 1, and then after that it just will increase. So if I did 2 to the power of 1, it's just a 2. 2 to the power of 2 is 4, and I could go on and on. I could go 2 to the power of 3, and that would give me an 8, because it would be 2 cubed. So like I was saying, if my x value kept getting smaller, if I did 2 to the power of negative 5, that's going to be 1/32. So that number then is getting smaller and smaller and smaller, and I could keep putting in there. I could put 2 to the negative power of 1,000, or of negative 1,000. And that number would get smaller and smaller, closer and closer to 0, but it's never going to touch 0. So what happens then is that you actually will have, when you go to graph this, you will have an asymptote at that 0. So my 0, 0 line is right here. There's my axis, so I would have an asymptote there. And then if I go to draw my actual values that I did here, these are going up by, what do I have them at? 5, 10, 15, 20, so they're going up by 5s. So at 2 to the power of negative 2, I had a 1/4, so about right there. 2 to the power of negative 1, I had a 1/2, and this is a little bit exaggerated, but it's hard to make my dots really small on this. At power of 0, it was at 1. At power of 1, it was at 2. At 2, it was at 4. At 3, then, it was up at 8. So, about there. And then if I continued going on, if I picked, like, well, 2 to the power of 5 here, I'll jump up to that one, is the same as 32. So 2 to the power of 5, which would be right along the axis here, will be 32. So this is 20, 25, 30, so it will be about right there going this way. And my graph would just continue going on and on and on. So if I were to draw this, it would go like this. Continue, whoops, pretend it went through that button, just continue going up. This would get closer and closer to that asymptote, but it would never cross it. So your domain for this would be all real numbers. I can use any x value that I wanted, positive or negative, and even 0. My range, though, it's never going to touch that 0 line, so your range is going to be everything greater than 0. Your asymptote, then, is at y equals 0. So that works when you have a whole number base. What if you have a fraction base, or a rational number as a base? Well, y is equal to 1/2 x is the same as saying y is equal to 2 to the power of negative x. That just makes it a little bit easier to do some of your solving. So if I try with the table of values here, if I used a 3, and x is a 3, I have 2 to the power of negative 3, that's 1/8. If I try a 2, 2 to the power of negative 2 is 1/4. 2 to the power of negative 1 is 1/2. 2 to the power of 0 is 1. If I go negative numbers now, 2 to the power of a negative 1 is like 2 to the power of positive 1, so it's just going to change that sign, so it's a 2. If it's 2 to the power of negative 2, that's going to be 4. 2 to the power of negative 3 is going to be 8. And this will go on again forever and ever and ever, right? So what's happening here when it's a fraction is the opposite of what happened when it was a whole number. As my numbers got larger in this case, as my x values got larger, my output value, or my y, got a lot smaller. Got closer and closer to 0, but didn't touch 0. So that would mean, again, I would have an asymptote going through my x. And then when I go to plot my points, at 3, it's 1/8. At 2, it was 1/4. At 1, it was a 1/2. And again, these numbers here are kind of a little exaggerated because I can't get close enough to my dotted line there. At 0, it was at 1. At negative 1, it was at 2. At negative 2, it was at 4. So it's almost touching that line. At negative 3, it was up at 8. And then it would just keep increasing, increasing. At negative 4, it would be up at 16. So like that, and then so on. So if I connected my dots here, they're going to go through these lines. They're going to get close to that 0, and then just continue going up and out. So if I look at my, oh, that didn't copy on here, my domain, I still have x as an element of real numbers. My range is still y is greater than 0, but not touching it, and my asymptote is just y is equal to 0. So same thing. Sometimes in the answer book it might write your range, it might write it as y such that y is greater than 0. And then it'll say y is an element of real numbers. So right below the sunrise, and it just didn't fit into mine, so I had enough space, so I just put it on the next page. It's basically just the summary of graphing exponentials. So when c is greater than 0, so when it's a whole number basically, y will be increasing if c is greater than 1, so if it's a whole number, so increasing means that it's getting larger from going from left to right across your x-axis, that it will be decreasing, or considered to be a decreasing function, if it's between 0 and 1. So if this, my fraction here is between 0 and 1, then my function is going to be decreasing, which means my values are going to be getting smaller as I go from right to left. And it's neither decreasing or increasing if c is equal to 1. Because no matter what, if this base here was equal to 1, it won't matter what I put in as my exponent. 1 to the power of anything is just 1. So if c was less than 0, so any fractional value, it's going to be a decreasing function. They're always going to have a domain of real numbers, and the range is always going to be greater than 0. It'll never cross that x-axis. They will have a y-intercept of 1, because no matter what your base is, when you put it to a power of 0, when that x is a 0, to find the y-intercept, it's always going to equal 1. It'll never have an x-intercept because it's not crossing that x-axis, and has a horizontal asymptote of y is equal to 0. So that's basically section 7.1 in your textbook, summarized in 2 examples. If you remember these key things here, then that's basically all there is to that part of it. It'll just apply it in a few different ways, but it's always going to be the same results. So section 2 then is doing some transformations of functions. So just quick transformation review. Remember the a value here is a vertical stretch. Your b value is your horizontal stretch. The h value is your horizontal translation, so it's that horizontal translation going left or right. And the k value is your vertical translation going up or down. So on the exponential graph, it's not a lot different. Your a value is still going to be your vertical shift factor. Your b value is still going to be your horizontal, or not shift, stretch factor. Your h value is going to be what's in that exponent, and that's going to be your horizontal translation of your left or right, and then your k is going to be what's added or subtracted, and that's going to give you your up or down. Okay, so graphing these transformations. If y is equal to 1/4 of 2 to the negative 1/2 x plus 1 minus 3. So you always have to take a look at this, and before you do anything, is figure out what is your base. So the base is what is the value that that exponent is being applied to. So this is our base. So I know it's a base of 2, so I know that it's greater than 1, so I'm going to have an increasing graph. So that means it's going to be going larger. Okay, so now what I do is I identify my A, B, and my C, or my A, B, your C value is the base, it's the 2, we've already done that, and then your H and K. So my A value is 1/4. My B value is equal to that negative 1/2. My H value is equal to 1, and because it's positive, it's going to go 1 left. And my K value is equal to negative 3, so it's negative 3 down, or just 3 down. So since my A is equal to 1/4, my vertical stretch factor is 1/4. My horizontal stretch factor is always that 1 over my B value, or 1 over the absolute value of B. So that means this is 1 over 1/2, so this is a value of 2. That negative in here means that it's going to reflect in the y-axis. Okay, so we always look at what is our base graph. So our base graph for y is equal to 2x. Okay, this our whole equation or exponential equation was 1/4 times 2 to the power of negative 1/2 x plus 1 minus 3. But the base of this graph with a base of 2 would just be 2 over x. So if I did my table of values for this, so at negative 2 I'd have 1/4, negative 1 I'd have 1/2, 0 I'd have 1. At 1 it would be 2, 2, 4, 3, 8. So those are my basic values. So I need to do my transform graph, and you could draw your basic graph on here if you want to help you, but you don't have to. A good acronym to help you remember what to do is called RECT. So RECT means that you do your reflections, you do your expansions. So those are your vertical stretch factor and your horizontal stretch factors. Then you do your compressions. So you squeeze them if you need to. I guess this should be this way. Expansion would be horizontal and compression is your vertical. And then T is for translations. So remember before we always said you have to do your A and B values before you can do your H and K values. So in my transformed graph, my reflections then are, in this case, it's only the B value that has that reflection because the B has a negative 1/2. If the A value was a negative 1/4, then we would be doing both of those. So for my reflections, X was a negative 2 in here, so in my reflection, because remember that's that bx value that's changing, your y, because we have nothing, no negative a value, then we just leave it like that. So I apply the r value, or the b, and it's just the sign of the b that we're looking at, so the sign of the b is negative, so that makes this into 2, and this stays 1/4. Negative 1 becomes positive 1 and 1/2. 0 becomes, or stays 0 and 1. My positive 1 becomes a negative 1 and 2. And then my positive 2 becomes a negative 2 and 4. And I'm kind of running out of space there. That should be negative 2 and 4. I'll squish it, my next ones together. So my expansions then. The expansions then are actually going through and using the B and the A value. So this is then actually doing the BX and the AY. So my B value was 1/2. But when I look at the horizontal stretch factor, B was a 1/2. When I put it into horizontal stretch factor, it was a 2. So I'm going to multiply by that 2. So that means that this is, for this particular equation, it's going to be a 2 times my x, and then my a value is a 1/4, so it's going to be 1/4 times y. So this is for the e. So 2 times 2 is 4. 1/4 times 1/4 is 1/16. 2 times 1 is 2. 1/2 times 1/4 is 1/8. 2 times 0 is still 0. 1 times 1/4 is 1/4. -1 times 2 is -2. 2 times 1/4 is 1/2. And then -2 times 2 is -4. 4 times 1/4 is 1. So my compressions then. Compressions are that the x plus h, sorry, I did these together. Expansion and compression are done together because they're the vertical stretch factor and the horizontal stretch factor. So those are taken care of together. And then my t is my translation. So the translation translation then is that x plus your h value and y plus the k value. So my translation then, in this case it's going to be x plus 1 to the left. So if it's 1 to the left, that means it's a -1. I'll just put this like this as a -1. And then, so for this one it'll be x minus 1, and the y value was 3 down, so it's going to be y minus 3. Excuse me. So in the first point here, it was a 4 minus 1, so that becomes 3. And then 1 over 16 minus 3. Well, that's going to give you a really wonky number, but basically it's going to be 2 and 15 over 16. -2, sorry, and 15 over 16. The 2 then. 2 minus 1 is 1. 1/8 minus 3 is -2 and 7/8. 0 minus 1 is -1. 1/4 minus 3 is -2 and 3/4. -2 minus 1 is a -3. 1/2 minus 3 is -2.5. -4 minus 1 is -5. And 1 minus 3 is -2. I didn't do the 3 and 8 just room-wise. You'll still be able to get the idea of what this graph is. So, if I go to draw this, my transform graph. So at +3, I was at -2 and 15/16, which is almost 3 and -3. So 1, 2, 3, these are going each by 1. So 1, 2, 3, and almost -3, so about there. The next one was at 1 and -2 and 7/8. So again, that's pretty close to 3, but if we put these into 16ths, this would be 14 over 8 over 16. So at 1, which is here, it's just a little bit more than that. That almost looks like it's at 1/2, but you get the idea. At -1, it's -2 and 3/4. Where were we at? -1. -1, it's -2 and 3/4. And again, this is off because of my dots get too fat. At -3, it's -2.5. At -5, it was at -2, so it's right here. And then it would just continue going on. The 3 and 8 point is actually at -7 and -1, so it would be right here. So you can see it's slowly curving up. It's increasing, which is what it should be because my base here is greater than 1. So just continue in that direction. And in this direction, it's going to get closer and closer and closer. So you can see my values were getting closer and closer to that -3, but they didn't touch the -3. So my horizontal asymptote would be right there. So if I go to write in this information, x again is an element of real numbers. My range was y is a set of values that are greater than, not equal to though, that was a boo-boo. Oh, I'm frozen, there we go. Is greater than -3, so my asymptote is at y is equal to -3. You probably noticed this value here, my k value, and my asymptote and my range all have something in common. Okay, so let's try the next example. Y is equal to -4 1/2 x minus 3. So my base here is a 1/2, so that's in between 0 and 1. So if I take a look at my values, my A, B, H, and K, oops, sorry. My A is equal to -4, my B is what's in front here, and it equals to 1. My H is a 3, and my K is a 40. So that means I have a vertical stretch factor of -4. My horizontal stretch factor is just 1, because my B value is a 1. This means that I'm going to go 3 to the right, and this means that I'm going to go 40 up. This A value had a negative in it, so that means it's going to reflect in the x-axis. So my flip then will flip across that x-axis. Okay. So your base graph then, remember when it's a 1/2, that's the same as saying is equal to 2 to the power of -1. So if I think of my base graph of y is equal to 2 to the power of -1, then it would be 2 to the power of -x. So that is my base graph. So if I do my x and my y values, if x is equal to -3, then this is going to be 8. If it's -2, it's a 4. If it's -1, it's a 2. 0 is 1. 1 is 1/2. 2 is a quarter, and 3 would be 1/8. So if I do my transformations again, my R, so this time because it's a reflection in the x-axis and it's the A, then that means that it's the y value that will be affected. So I'm going to do these in the 4 steps. You don't need to. You could do them all at once. And I will do one where I do them all at once so that you don't have to actually, no, I won't, because I'm only doing them for these 2. I'm only doing graphs for these 2. But you could do them all at once. So if you're doing them all at once, then remember it's just that bx plus h, ay plus k. So for my R, that's my reflections. The only thing that was reflected in this was that Y. So anything for my Y values here are going to have opposite signs. So this will stay -3, but it becomes -8. This is -2, -4, -1, -2, 0, -1, then it's 1, -1/2, 2 and -1/4, and 3 and -1/8. My expansions and my compressions. So my expansion is multiplying by 1, and then compression is multiplying by 4. So that's actually multiplying through with the B and the A values. So this was a 1, so times 1 times 4. So the X times 1 and the Y times 4. So this becomes, all my X's then just stay the same because they're multiplied by negative, or just by +1. -8 times 4 is -32. So -2 and -4 times 4 is -16. -1 and -2 times 4 is -8. 0 and -4. It's going to be 1. 4 times -1/2 is -2. The 2 stays the same. -1/4 times 4 is -1. 3 and -1/8 times 4 is -1/2. And then finally my translations. So that's going to be, for the translations, the X values are +3 and the Y values are +40. So -3 plus 3 is 0. -32 plus 40 is 8. -2 plus 3 is 1. -16 plus 40 is 24. -1 plus 3 is 2. -8 plus 40 is 32. 0 plus 3 is 3. -4 plus 40 is 36. 1 plus 3 is 4. -2 plus 40 is 38. 2 plus 3 is 5. 40 minus 1 is 39. And 3 plus 3 is 6. And -1/2 plus 40 is 39.5. So now if I go to graph these, once I've done all of the expansions in here, I would have 0 and 8. So 0 and 8. Where am I? Yeah, that's pretty close. And then I have 1 and 24. 2 and 32. 3 and 36. 4 and 38. 5 and 39. 6 and 39.5. And then it would just keep going. It would be 7 and 39 and I think it's 39.75. I can't remember exactly what the value will be. But you can see then my graph is now going close to that 40 and then going down. So it was the flip. There's my reflection in the x-axis. It flipped over my x and was transformed. My asymptote then, it's getting close to that 40 value, but it's not crossing it. So my domain, x is an element of real numbers. My range, it's everything. Whoops, I went the wrong way here. because of that translation, it's not greater than 40, it's less than 40, and my asymptote is at 40. So it says, can you predict the asymptotes and the ranges, that should be the ranges, of these exponential graphs? So, knowing in the other two graphs that we did, that k value told us what the range and asymptotes are going to be, then we would know from here that our range is going to be y is greater than 7. I don't have a negative for that a value, so that means that I'm not going to have any translation. My asymptote then is y is equal to 7. Okay, if I take a look at this one, my a is equal to 5, so I don't have any reflections going on there, so I know my range is going to be a greater than, that's a value of negative 2, so your asymptotes then are at negative 2. In this graph, my a is equal to a negative 1/2, so that means I'm going to have a reflection, so that's going to flip my sign. This is going to be y is less than negative 3, and my asymptote will be at negative 3. Okay, so the next part is what if you're given the graph and you want to find transformation. Here it says, hint, you need 2 points, and y is equal to ac b, or to the power of b times x minus h plus k. And it can be simplified to y is equal to ac x plus k. So if I take a look at this, I know in my normal graph, if I just had y is equal to a to the x sorry, not a to the x, c to the x, whatever that is. So if it was a base of 1, a base of 2, base of 3, doesn't really matter. My normal graph would go through you know, it's always going to have, I'm just trying to see where's my values here. This is 1, 2, 3, 4, 5, okay? So it's always going to go through 0 and 1. No, I'm just going to pause here because I won't want to mess up that equation. Okay, sorry. I just wanted to make sure I wasn't leading you astray. So we need to find what the base function is. So in order to do that, you can't just draw on there your base function y is equal to y is equal to b or c to the power of x. But what you can do is figure out what the c is. So what you need to do is you need to look at your graph and pick the points where it is exactly crossing at intersections where it's not just halfway in between points. So one of those spots is right here at 2 and 3, so 2, 3. I already put the dots on there for you. So 2, 3. Over here at 3, we have 3 and 7, I believe that is. Did I get that? This is 0, 0 here, so 1, 2, 3, 4, 5, 6, 7, yep. So 3 and 7, and then this one here occurred at 4 and 15, 16, 7, 15, 16, 17, 18, 19. So 4 and 19. So if you take a look at these, from that first point that we found there, it started at 3. The next one and I'm just looking at the y values. Went from 3, then it went to 7. And then from 7, it went to 19. So this was a difference of 4. That was a difference of 12. So that means that our C value went from a 4 to a 12, so then it was a multiple of 3. So that is our C value. The base value for this will be a 3. In your original graph, when we were doing y is equal to x squared, if you want to think of that one, it was over 1 up. Oh no, sorry, not your y is equal to your just your bx. It would be over 1 up 2. And then over 1 up 6. So our original graph would be over 1, I can't draw it on there right now because it won't make sense, up 2, and then if it was a base 3 graph, I mean, it would be over 1 up 2. Okay, for our base graph, we did I'll just write it in so you can see what I'm saying. If it was a 0, it would be 1. If it was a 1, it would be 3. If it was a 2, this would be 9. So our base graph would be at 0 and 1, which is here. This is kind of confusing because this is your 0 down here, not right there. So 0 and 0 are here, so this would be 0, 1, and then 1 and 3. So 1 is here, 1, 2, 3 would be there, and then 2 and 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9 would be there. So it would be going like, oops, this for your base graph. So this is y is equal to 3x. So in that case, we went over 1 from our original and then up 2, because we started at 1 and we went to 2. And then we went over 1 and up here to 9. So if this was at 1, 3, and this one was at 2, 9, so that's where that comes from. So starting from here, from this point here, which was at 0, 1, we went over 1 up 2, over 1 up 6 to get to that 9. So that's actually then the base graph was doubled. Instead of going over 1 up 2, it was going over 1 up 4, over 2 up 12. So it's doubled. So then that means in order for that to double that, that means that your A has to be a 2. So this is my original, or I shouldn't say original, I'll say this is the base graph. So from the base graph to the transform graph, we doubled those up values. Instead of going up 2, it was up 4. Instead of going up 6, it was up 12. And it would continue. And I know what my A value is, and I know what my C value is. Graph then, or my equation right now, would be y is equal to an A value of 2. My C value is 3. I don't know my b at this moment. And my x minus h, don't know those. But I do know from looking at this graph that I have a k value. This graph here, because I know this is 1, and based on the look of this graph, I know that it can't be touching that positive 1. So my k is equal to 1 because that's my asymptote on there. My graph gets really close to 1, but it's not touching it. Okay, so now we need to find a point in order to solve the rest of this. So I'm going to pick a point. So I'm going to pick point. In this case, I'm just going to pick 2, 3. So those are x and y values. So I can substitute those into the equation that I have right now, and that will give me my x and y in there so that I can find my other values. Okay? So before I do that though, we can do the b value. If I look at my b value in here, every time I did this, my shift over was always just 1. I did to 1, and then to 2, and then to 3, and then to 4. Well, I couldn't use the 1, sorry, because it was an asymptote there, but it went 2, 3, 4, and then I would go 5, and so on. So that means because there is a horizontal stretch factor, I didn't go over 2, over 4, over 6, or anything like that. It was always 1, 2, 3, 4. So my b is equal to 1 because there is no horizontal stretch factor. So I could then rewrite this equation here would be y is equal to 2 times 3 to the power of x minus h plus 1. Okay, so now let's find that h value. So I pick a point. My point is 2, 3. And I substitute. So this is 3 is equal to 2 times 3 to the power of 2 minus h plus 1. So if I subtract 1 from both sides, I have 2 is equal to 2 times 3 to the power of 2 minus h. Okay, and then I divide by 2. I didn't leave a whole lot of room here, so I'm going to go sideways. I'm left with 1 is equal to 3 times, or to the power of 2 minus h. So I know in order for this side here to equal 0, or sorry, to equal 1, then my exponent has to be 0. Okay, so for my answer to be 0, or sorry, to be 1, I know that my exponent has to be 0. So what this is saying then, it's like 1 is the same as saying 3 to the power of 0 is equal to 3 to the power of 2. So if I have the same base, I can just drop that off. 0 is equal to 2 minus h, so h is equal to 2. So now that I found my h value, I've got everything. So my final equation then is y is equal to 2 times 3 to the power of my b was a 1. So I'll just write it in here for this time because sometimes your b isn't going to be a 1. Times x, my h was a 2, so that's minus 2 plus 1. Okay, so when you're doing these, then what you want to do is you're going to look at, well, you could do the stretch factor if you wanted first. So pick points that are exactly on both the x and y. So look at, and start at 1, or depending on where you can see the asymptote. So this one had an asymptote at 1, so I'm not going to start at x is equal to 1. But I did find that I had an exact point at 2, when x was 2, when x was 3, and when x was 4. So then you write down what those points are, and then you can see, okay, if it's going 1, 2, 3, 4, then I know my b value is a 1 because I haven't stretched that at all. Then you can take a look at your compressions, or your, what is your c value for this? So take a look then to find your c value. What's your base going to be? So I went from 3 to 7, and then 7 to 19. So 3 to 7 was an increase of 4. 7 to 19 was an increase of 12. So to go from 4 to 12, that was a 3. So I know then my c value, which is the base for the exponent, is a 3. So once you know what your base value is, then you can figure out by doing y is equal to the base of x and substitute in there and draw that. So that's what I did there. And that's when I drew this. So this was my base graph using that. So then from my base graph, I look at what did I do on those stretches going up. So I went from 1 to 2, or sorry, I went over 1, up 2, and then I went over 1, up 6. So it was an increase of 2, and then an increase of 6. So if you then you compare, okay, what was that increase to the original? And sometimes it might be exactly the same. So if that was a 12 and a 4 in this, then it would, my a value would have just been a 1. But because it went 2 and 6 instead of 4 and 12, then I know it doubled, so my a is a 2. So once you've got those two, you can substitute those in. Take a look at any shift that you did. So this one shifted up 1. Okay, I wasn't crossing that 1, so everything moved up 1. So I have that value. Pick a point, substitute to find your h, and you're done. It says, caution, you may end up with one of the many equivalent forms. So what that's saying, this is the way to write this. Okay, sometimes with fractions, if they put this as, or they could put a negative in there, especially with this example down there where there's a fraction in there, so they might not write it in that form, or when you solve it, it might not look exactly like that. 1 to the power of 27 is the same as 1 over 3 to the power of 3. 9 then could be written as 3 squared x plus 2. So this and this are the same equation. They're just written with powers instead of writing them in fractions. Because this then can be written as 3 to the power of negative 3 times 3 squared to the x plus 2. It's the same equation. Okay, problems. So hopefully this will go a little bit quicker for you. A cup of water is heated to 100 degrees Celsius and then allowed to cool in a room with air temperature 20 degrees Celsius. The temperature is found to decrease by 25% every 5 minutes. Find an exponential graph to model the temperature of the water and use it to predict the temperature after 15 minutes. So we're starting at 100 degrees. It's staying in a room with the air temperature of 20 degrees Celsius. That doesn't matter. What they found out is that the temperature decreases by 25% every 5 minutes. So if it's decreasing by 25%, then 75% of the temperature of the original temperature remains after 5 minutes. Oops, I should say remains. So I know then my base for this my starting is at 100, okay? And my change is happening every 5 minutes, and it's a 75% decrease every 5 minutes. So that stretch value, if you want to think of it that way, or the vertical stretch here is being affected by that 100 degrees. So that is your A. %75% is the amount of change that's happening. It's going to be multiplied by that 0.75 every time. So that is your, if you want to think of it, that's your exponent. Every 5 minutes, it's going to change. So if you think of it, every 5 minutes, if we did 3 intervals, then we would have 3 5-minute intervals, or 15 seconds or 15 minutes had gone by. So if we wanted to write this out, we'd have y is equal to that 100 degrees, that's the base temperature, or the original temperature, I guess I shouldn't say base temperature, and it's changing that 0.75 every x. So every interval, every time we check it, it's going down that 0.75 from the original temperature. So the original temperature was 100, it's going down 0.75 of that, or you're left with 0.75 of that every interval. So you have to stipulate here that where x is in 5-minute intervals. So that would mean if you had 3 intervals, then you would have gone 15 minutes in time. Another way to write this, if you wanted to do it in 1-minute intervals, then you'd have the same original starting temperature with this in that 0.75, but because we want to do it per minute instead of per interval, we would divide by 5. Okay, so in the first one we're saying we're just going in intervals, so that would be x is every 5 minutes, so if I had 2x then I would have a 10 there. If I had 3x I would have 15. The other way is then, is if I'm saying where x is the time in 1-minute intervals, then I'd have 1 over 5, 2 over 5, and so on. So after 15 minutes, that's 3 intervals. So if I'm using the first equation here, I'll call this y1 and this y2. This would be 100 times 0.75, where x is in 5-minute intervals. So if it's 15 minutes, that is 3 intervals. Or if I did the other way, y2 is equal to 100 times 0.75, 15-minute intervals, so that would be 15 divided by 5, so it's still 3. It's still the same thing. So when you put this into your calculator, what you'll find is that your answer is, what is the temperature after 15 minutes? It would be down to 42.2 degrees Celsius. Okay, the next one says the half-life of AM-241 is 432 years. If a smoke detector has 200 UGs, and that's the short form for micrograms. You might have taken that in bio or chem, of AM-241 in it. Create an exponential function to show the amount that would be left in of AM-241 that would be left in the smoke detector at any given time. Okay, so our starting value in here is 200 units. So I know that that is my A. That is my starting value. The half-life means that every 432 years there's going to be half as much in there. So that is the exponential base. It's decreasing by 1/2 for however many years you have. So this would be to the power of x, where x is in 430-year intervals. So one interval is 432 years, two intervals would be 864 years. So the other way would to write this in yearly increments. Y is equal to 200 times 1/2 x over 432. So this would be where x is in 1-year intervals. Okay, so this one, they've given us that Y value in the second part of this question. If the smoke detector needs at least 180 milligrams of this to function properly, how long, sorry, not milligrams, micrograms, how long will the smoke detector last? So if you have 180, or if you can't use less than 180, how many years is this smoke detector going to be effective? So we have 180 is equal to 200 times 1/2 x to the power of 432. So you need to do this on your calculators. So 180, first thing I'm going to do is divide through by my 200. And I didn't write the math down for this on mine, but you're going to have a fractional value. So you're going to have, let me see if I have a calculator here. 180 divided by 200 is 0.9. So I have 0.9 is equal to 0.5 x to the power of 432. And this, unfortunately, the easiest way to get this one is just trial and error. You're just going to plug in some values in there to see what you get. So you can start with some small values like trying 10 divided by 432. So 10, that would be 10 years that this took, not 10 intervals. That wouldn't be 4,320. It would be 10 over 432. And then you just keep trying, and you'll see if you start 10, well, your number is off. So when you keep doing this, the way to solve this is using logs, which we don't do just yet, so that's why we do trial and error. So you'll find, when you finally get the right answer, it is 65.67 years. So if you try it in your calculator, if you did 0.5 to the power of, you'll have to put a bracket, 65.67 divided by 432, in your bracket, it's about point, and I must have rounded wrong in my final answer. Oh, I just put something wrong in here. It's about 0.8 something, so it's close. So it's probably, this might be a better choice than that one. It's all in the rounding. So that's it. Good luck.